Thank you, Maria. Thank you, Peter, for the introduction. Good morning. I'm Andres Litvak. I currently work at CEREMAC, which is a French public center of expertise on sustainable planning. And I used to work at CDP and APEBAT when the FREEVENT project started in 2014, 4 years ago. Today, it's my pleasure to present the results of the FREEVENT project on ventilative cooling and summer comfort. This project is led with my partners ALLIE'AIR, ACA-O, and ALDES, and it's partly financed by ADEME. Mainly, well, I will briefly give a brief presentation of the FREEVENT project, which deals with field measurements of summer comfort and evaluates the efficiency of ventilative cooling in French residential and office buildings. The objective of this work is to quantify and qualify the efficiency of the ventilation systems and the energy and thermal performance of buildings. For these 2 field measurements campaigns were conducted, ventilation checks on 9 sites and full measurement and monitoring on 6 of them. So our study concludes with recommendation guidelines for designers and published a French guideline which is downloadable on the French platform. Well, it's an international platform. It's construction21.org, but it's in the French part of it, since the guide is in French, and it gives all the results of our work and recommendations on design and for designing and installing ventilative cooling systems. The results of our work will be presented at the AVC conference in Jean-les-Pins in September in an English paper. So for those of you who don't speak French, you'll be able to have a publication in English in September. Well, so as I said, my presentation will focus on the theoretical approach of comfort and energy performance of ventilative cooling. And the presentations of my colleagues, Anne-Marie and Nicolas, will give more operational recommendations for designing and installing efficient ventilative cooling systems according to the observations and knowledge we got from field measurements on the field measurement study we did. So the major concerns of ventilative cooling are mainly the heat wave periods that are more and more frequent, and the associated increase of mortality is a real issue in terms of public health. Non-air conditioned new or refurbished buildings that show more and more summer overheating issues, mainly due to loads containment. And last, providing summer comfort without air conditioning becomes a real challenge for energy transition politics, and one wants to go into bioclimatic architecture and passive house buildings. So ventilative cooling depends on thermal energy evacuation capacity from a hot evening to a comfortable morning, taking advantage of the coolness of the night. So the main issue is to correctly design the ventilation cooling in order to have a not too hot or not too cool indoor environment in the morning, as you can see here in the slide. For our work, we defined concepts such as thermal potential and energy evacuation. As you can see here in the graph, the thermal potential is defined here in green color between the curves for 2 nights. The first night is from a heat wave, and the second one is a cooler night. Here, we can see how important it is to account for the weather conditions and to design an adapted regulation for ventilative cooling, making the regulation whether manual or clock-based or based also on temperature probes. So you can see that you have to adapt the period of the ventilative cooling to have the better result. And you can see that the second night you have a potential twice as higher for the first night, which took place on a heat wave. So mainly the objective of a correct ventilative cooling design is to evacuate during the night the increase of the temperature that occurs during the day, and for that you have to have a correct design. The main challenge, as a matter of fact, is to provide comfortable conditions with an optimized energy approach. For that, we use the EER coefficient, which is the energy efficiency ratio, which is the ratio between the cooling energy provided and the electrical energy necessary to produce the coolness. So for a natural ventilation system, you have no electricity, so the EER is equal to an infinite number. Whereas for mechanical ventilation, this ratio, the EER, is usually known to be between 4 and the value of 10. But what we want to point is that the EER optimization depends on evacuation potential, and performance EER doesn't mean necessarily that the ventilative cooling is efficient. So you have to make the balance between the energy performance and the real comfort that is provided. So for that, when one wants to optimize the thermal and comfort performance through ventilative cooling, you have to handle both parameters, so the potential of evacuation and the energy efficiency ratio, the energy performance approach. And for the comfort, you have to account for the parameters that's related and that can disturb the comfort, which are mainly the temperature. You can have overheating if you cannot provide enough coolness during the night. But you can also have times when in the morning it's too cold, and it can be discomfortable. Other issues of comfort are acoustics, we'll see it later, and air velocity in the premises. Of course, the bioclimatic architecture provides some hints to make adequate design for ventilative cooling. Well, I will not go on the definition of thermal comfort that most of you may be aware, but it depends on the activity clothing and adaptive comfort, and it's generally taken between 27 and 28 degrees Celsius. That's what we did for our modeling, that Nicolas may explain later. What we took into account as a parameter is the acceptable numbers of hours beyond the discomfort threshold. Caution is to be given for discomfort in the morning. That's what I say, that perhaps sometimes you may have cold mornings, too cold mornings, which is not what you want to experience. And also for residual air velocities, if ventilation occurs during building occupancy hours, due to the elevated airflow rate. So for acoustic comfort, well, you have to take into account if the building is occupied or not, because if it's occupied, you may experience noise exposure zones as regarding to doorway openings for natural ventilation, or in case of mechanical ventilation, equipment noise and air velocity may produce some discomfort. On the other hand, for unoccupied premises during ventilation cooling period at night, mechanical ventilation may produce with the equipment noise towards neighbors that may be a problem. And in all cases, occupied and unoccupied, acoustic treatment of the transfer grid is necessary to maintain adequate airflow transfer through the whole premises. Another issue is indoor air quality, since ventilative cooling may impact, will impact indoor air quality through increased air change rates. While it has a positive impact in the majority of cases in non-polluted environments due to the increase of the dilution of the indoor pollutants. But the caution must be given for preventing outdoor pollutants penetration from outside in case of industrial zone, road traffic, and airports, and the necessity of filtration and forced mechanical ventilation equipment. So it has an impact on the energy performance of the system. For noise and indoor air quality, you can rely on some public resources in France. For example, we have maps that are provided by local authorities for the noise exposure, or for agencies for indoor air quality on some pollutants. So you can use this type of documents of resources to better design your system. And for bioclimatic architecture, the challenge, the main challenge of ventilated cooling is to unload in a brief summer, especially cold nights, all the accumulated heat during a hot, long day, so then preserve coolness as long as possible. The action levers for that are designing proper solar shading, thermal inertia, and insulation. We will see that height of premises due to stack effect and warm air certification is an important parameter, and of course the limitation of internal loads. So for that later case, we quantified by simple modeling tools the impact of the potential of different buildings to accumulate the heat during the day and to evacuate it during the night. I will let Nicolas Pio give more explanation about the simulation later, but as a first approach, one should evaluate where the major loads, internal, solar, and according to the airflow rates, the differential temperature, delta T, and the duration of the ventilative cooling, what are the orders of magnitude for optimizing the potential of the ventilative cooling? So this first approach will help us to have an idea of the order of magnitude of what can be done in terms of potential of energy evacuation and ventilative cooling. But ventilative cooling will never be able to correct a bad design if internal loadings are too high. Also, for the thermal inertia and insulation is a concern, of course, in order to take into account the thermal shift and damping that is potentially provided by the inertia of the building. In all cases, external envelope with high inertia is recommended, but one should know that the occupational scenario of the building is important because, for example, for an office, usually the building is unoccupied, so that makes during the ventilative cooling period, whereas for dwellings, it's usually occupied by people sleeping. The occupants are sleeping, so one can optimize the inertia in order to have the correct comfort parameters during the night and the morning. Here you can see on the curves, according for two different types of buildings with different inertia, with heavy building in violet and light building in blue, that you can see according to the occupation mode what you want to have with the shift, the thermal shift and the damping. Another point is as I mentioned, is the stack effect height for natural ventilation, which make due to warm air stratification, the comfort zone it can be occupied or not. So it's better to have a tall height in order to have a cooler occupied zone, as you can see in the figure. And last point is the ventilative cooling airflow rates that depend mainly on the cooling potential of the site. Our modelings for two different towns in France, Macon and Montpellier, that have different climatic conditions, show better results of 1 air change per hour in Macon and 4 air change per hour in Montpellier. So you can see that the same building in different places may show a ratio of 1 to 4 to give the good comfort conditions. Usually one should aim at 2 to 6 air change per hour. Here you can see in the graph the comparison of outside temperature and the potential of energy evacuation. And for the city of Macon, in green and the blue zone, the potential is 4 times higher than for Montpellier. Also, we did some modeling by changing the airflow rates for the same buildings and show that, as I mentioned, the ratio of 1 to 4 on the airflow rates to have correct comfort conditions. And last, we did some simulations for office building in the city of Toulouse, and we shown that the average number of discomfort can strongly, significantly vary according to the airflow rate that is simulated. So from the regular hygienic ventilation gives more than 7,000 hours average discomfort per year, whereas for a 6 volume per hour, you can go to a little bit more than 80 hours per year. So the key points of success are upstream bioclimatic design. Ventilative cooling will not compensate a poor design of internal and external loadings, as I mentioned before. So you have to adapt to dimensioning that accounts for all comfort criteria. And as we will see with Anne-Marie's presentation, involvement of owners and maintainers and also of occupants in the first years for fine-tuning operation is essential. So I'll finish with my presentation. I will take questions if we have enough time. And I will re-mention that, well, our guide, which is in French, is available on the construction21.fr website. And thank you very much.